Hello everybody. Today I will present the polar decomposition of complex matrices as explained in the book Les maths en tête by Xavier Gourdon. Let us start with some definitions. An n times n matrix is unitary if U transpose conjugate times U equals the identity. The notion of transpose conjugate is relative to an inner product, so it's not surprising that you have this characterization that U preserves the scalar product. This is the complex analogous of what you have for real rotation matrices. Two other comments: if you preserve the inner product, then you preserve the norm. So if you are unitary, then you are an isometry. It is just that isometry is for the general framework of metric spaces, and they don't have to be linear. Second comment: if you are in infinite dimension space, you will have to add this condition that U adjoint equals identity. Second notion: a matrix H is Hermitian or self-adjoint if H transpose conjugate equals H. Equivalently, you have a characterization in terms of scalar product. By definition of adjoint, you have the equality. So here normally it's the adjoint, but the adjoint equals to H. Conversely, if you want to go from this condition to this condition, you simply take x and y to be the canonical basis element. So I call EI the vector that has component 0, 0, and then in position E in the line, the eth line, it has a 1, and then the rest is 0. It's a vector like this. If I take here the vector EJ, here I take EI, I will obtain here H applied to EJ, it's the jth column. I just write like this, the column of H, jth column, and here is the vector EI. Here it will give the element in line I and column J. Here, if I have EJ, and here I have column I, because this is a sesquilinear form, it will give CI EJ and then complex conjugate, and this is the column I, line J, and complex conjugate. So here we recognize that H transpose conjugate equals to H. Last notion: a matrix P is positive if it can be written as a kind of square. I do not say, but in fact positive is necessarily self-adjoint. It's self-adjoint plus another condition that this quadratic form is positive. We can see it as a quadratic form in X. I will not show the equivalence, but here you can see one implication is that if P equals to R star R, I replace here R star R, X, scalar product, inner product, and here we recognize a norm square. It will be norm square of R of X, so it will automatically be positive. So this condition will imply this condition. Let us now state the theorem. For any matrix A, there exists a unitary matrix and a positive matrix such that A equals UH. This is the analogous of what you have for complex numbers. You can write as exponential I times the angle times the modulus. H is the modulus. In fact, U is called the phase and H is called the absolute value. And a unitary matrix, you can show that it can be written as exponential I times a self-adjoint matrix. So it's really like the complex polar decomposition. If A is invertible, then this pair is unique. The proof goes in 2 or 3 steps. First, we define H, and second, we define U. H is characterized by this condition, and then we have to separate in 2 cases. Whether A is invertible, then U will be completely fixed. There's no other choice, because if we have If we want to have this condition and A is invertible, we can show that with this condition H will be invertible, and if we multiply by the inverse on the right, you will necessarily have this condition. If you want this to be fulfilled, you must take U equal this. Yeah. If A is not invertible, then you define U on different subspaces, and you will see that it is fixed on this space, but here you will have a choice. A second method is to approximate A with invertible matrices for which we have the polar decomposition, and find a way to find convergent subsequences, and then you have to show that each subsequences does converge to a unitary element, and here a positive element. So let us start the proof. If a polar decomposition exists, the H must satisfy this condition. I replace this UH transpose conjugate, it will give H transpose conjugate, U transpose conjugate times UH. Here, because U is unitary, this is the identity matrix. Because H is self-adjoint, this is just H. So H must satisfy this. Then the second step is simply to take the square root. So here I will make a digression on an abstract way where we could define a square root. You can skip if you are not interested. So let us notice that the square matrix is an algebra. You can add and you can multiply. So in fact, you can define a polynomial of a matrix. Here we are saying that there's a unique map that extends. You take any polynomial, you can have a polynomial into this matrix, but here you can extend to continuous function, and you can define a continuous function on the matrix. The spectrum is a set of eigenvalues. So here it's a sledgehammer to kill a bug, to crack a nut. Because continuity on a finite set is not any condition. You can take any function. In particular, because the spectrum is positive, you can take the square root. More concretely, n, that is a star a, that I denoted n. So you can see it is self-adjoint. It's equal to its adjoint. You use a theorem that it is diagonalizable in an orthonormal basis. So there's a change of basis matrix such that a star a is similar to a diagonal matrix. I call this matrix D. So again, let me give some details that you can skip. It's not a complete proof, but it gives some idea, some relation. So a matrix is diagonalizable. It means that it has a basis of eigenvectors. I will call them C1 to Cn, column vectors. To be an eigenvector, to be an eigenvector, it means that when you apply n, is just multiplying by some complex number. Here it's self-adjoint, so this number will be real. If I put those vectors as a column of a matrix, so first column here, second column here, third column here, nth column here, I can write all of this equality as an equality of matrix. So every time it just multiplies the vector by a scalar, so lambda 2 C2, and so on, lambda n Cn. And here we can also recognize as a product of matrices, column 1, column n, and it is multiplied by this diagonal matrix, lambda 1, lambda 2, lambda n, and the rest is 0. So if I decide to call this matrix P, I have NP equals P, and here's our matrix D. NP equals PD. Okay, let me show. NP equals PD. If we're able to show that P is invertible, then I multiply on the left or on the right this equality. If I multiply on the right by p minus 1, I get n equals pd p minus 1. This is my n equals pd p minus 1. If I multiply on the left, I get p minus 1 np equals d. So what is the interpretation of p? It's a change of basis matrices. It means that if xi, capital Xi, are the coordinate of the vector in that new basis, the coordinate in the original basis is related by this equality. X is p times xi. I want to point that the fact that B is a basis will imply that this map is a bijection, thus explaining that there exists p minus 1. Let us just detail this. Notice that if I apply p to a vector that I call xi, it has component xi1 and then xin, and then the matrix P is column 1, column n. This multiplication just, so this times this, this times this, this times this, just gives the linear combination sum xi, xi, ci. And this map, you can see that it is injective because a basis is free. So if this linear combination xi, ci, if this is equal 0, because the family ci is free, then all the components, all the coefficients, so from 1 to n, xi equals 0, means that this vector has to be 0. For surjectivity of this map, you use that this basis is generating. So for all vector in the target space, there exists vector xi in the domain such that v equals p xi, capital Xi. So this means that there exist coefficients xi such that the linear combination equals v, and this is surjectivity of p. So p being a change of basis is necessarily invertible, so we invert and get this relation. We can say more about the origin of this relation, is that a matrix is self-adjoint if it's semi-simple. It means if you have a stable subspace, then there exists a supplementary subspace that is also stable. Here we can even take F to be the orthogonal complement. Let us show this. I say stability of E for any vector V in E, n of V will be inside the subspace E. I just simply write like this. We want to show the same for the orthogonal supplement. Let us take two elements, one in E and one in the orthogonal supplement, complement. So when I apply ny, because n is self-adjoint, it gives nx scalar product y. Because this is stable, this is still an element of E. This is an element of E orthogonal, so this is 0. If we read for all x, x is perpendicular to ny, it means that ny is in the orthogonal of E. So we have stability of the supplementary subspace. In fact, the last ingredient to show that n is diagonalizable is to show existence of eigenvalue for every subspace. I will not do it here, but I want to add that, of course, if you are inside an eigenspace, you can choose an orthonormal basis, and if you have vectors in two different eigenspaces, they are necessarily orthogonal. So in fact, P, you can take it as the column of it are unitary of unit 1 orthonormal vectors, orthonormal eigenvectors. So in fact, P will be a unitary matrix. So I go back, we have diagonalized our matrix A star A, and here we add the information that n is positive. By definition, it means that a quadratic form is positive. We can check it immediately because in fact n is a square. So as before, you can write as a norm square. In particular, if I take x to be the eigenvectors, here I have a eigenvalue that pop out. This is positive itself, a norm. We know that the whole thing is positive, so we deduce that lambda I itself is positive. If it is positive, we can directly take the square root. Here you can have plus minus, plus minus, plus minus sign. It will still satisfy this property that its square is equal to A star A. You have unicity if you impose that those coefficients are positive. So there's a unique positive map matrix such that A star A equals H square. So we have this. Now we want to show that if A is invertible, then U is completely fixed. It goes in two steps. We have to show that if A is invertible, then this will be invertible, and H alone is invertible. Let us give 3 arguments for this last step. So by definition, an element, if you have a complex number lambda, n minus lambda identity, it is lambda is in the spectrum. If this is not invertible, if I take the negation, a minus lambda identity is invertible, so it means that this lambda is not in the spectrum. It means that the spectrum are composed of eigenvalues, so 0 is not among the eigenvalues. The eigenvalues are non-zero, so it means that those are non-zero. It means that H is invertible. You can directly take the inverse as 1 over this, 1 over this, 1 over this. It will give the inverse of H. Second argument is that if you have a composition of map that is bijective, then you know that F is surjective and G is injective. For example, for any element in the target space, you can write as f of g of something. So it is f of something. So f is surjective. Let me write the definition of injective for g. If we have g of something equals to g of something else, here I just apply f. So f of g of something will be equal to f of g of some other things, and because f of g is bijective, it is in particular injective, so we have x1 equal x2. So we have that g is injective. We use this for H composed with H. I here identify matrix and application. So if H square is bijective, then H itself is bijective. Last argument that can show the whole thing, so you take the determinant of this is non-zero because it's invertible, so the determinant of this is non-zero, so determinant of H itself is non-zero. If H is invertible, then you necessarily have this relation, U is A, H minus 1. It remains to show that it is unitary. I just plug this in the definition. This transpose conjugate will give H minus 1 transpose conjugate, A transpose conjugate. Here you have A star A is what we call H square. It compensates with each of those and gives the identity. So we have seen the unicity. There's a unique positive matrix such that A star A equals H star, and then because A is invertible, U is necessarily defined by this, so there's no choice. If A is not invertible, we'll see that there's a choice, but we'll start with this first remark that because of this relation, we can see that the norm of AX square can be written like this. By definition of the adjoint, you can write this like this, and A star A is H square, H is self-adjoint, so we have this relation. So we have that the norm of AX is equal to the norm of HX. If this is 0, then this is 0. If right-hand side is 0, then this is 0. It means that the kernel of A and the kernel of H, they are equal. You see that the modulus part, here's the part that multiplies h, that changes the length of a, gives the same length as a of x. We now use the fact that h is self-adjoint to cut the initial space as a direct sum. So you can understand this as the eigenvector for the eigenvalue 0, and here is the direct sum of all the other eigenvectors, eigenvalues, eigenspaces. We have seen, have just said that the eigenspaces are orthogonal to each other. So in fact, this is orthogonal to the rest. So the image is equal to the orthogonal complement of the kernel. So on this part, on the image, we'll see that U is completely determined, because on the element that is of the form H of something, U of this must be equal to AX. Does this define a does it give a well-defined map? So we have an element Y in the image. We want that when you apply U, it gives AX. But here you see that an element in the image, it could be written with two different forms. It could be h of something and h of something else. If it is the case, the difference here will be 0. So h of the difference of the two different pre-image is 0. It means that this is in the kernel. The kernel of h is equal to the kernel of a. So it means that, in fact, a has the same image. So you can define like this. You just pick any x that is a pre-image, then you define U of y as a of x. In fact, you can systematically choose, make a systematic choice. If you restrict h, notice that if you restrict h to a supplementary space of its kernel, then this map will be injective. It is surjective because we take the image as the target space. So the restriction h to a supplementary of its kernel will give a bijection, so I can have the inverse. So you see that here it is the same as when h was invertible. U is defined as a h minus 1, but it's just a restriction. You can take any restriction. It's the same as choosing a systematic way to choose a different pre-image, but this will be the same map. So now what does U do on the kernel? We have defined it on the image. For the kernel, we see that there's not unicity, but if we require U to be, if we look for a unitary matrix, it must satisfy some condition. If I have two orthogonal vectors, so this in this space, this in its orthogonal, then the image will have the same relation. So they are perpendicular, the image are perpendicular. But here we see that the image of this restriction, if y is in the image by U will be in the image of A. It means that if X is in the kernel, U of X will be perpendicular to an element in the image of A. So it means the image, it has value, it must have value in image of A orthogonal. So we just need to choose any isometry. Let us show that at least it is possible because those two spaces have the same dimension. How to prove? We know that those two spaces are equal. We use the rank theorem for the application A. The dimension of the kernel plus the dimension of the image equals the initial space, dimension of the initial space. So we have dimension of the kernel equals n minus dimension of the image. This is the same dimension as the dimension of the orthogonal of the image. So dimension of this equals dimension of this. And we see that we just have defined U on subspace that are in direct sum. So when you are in the kernel, you just apply an isometry. And when you are in the image, you apply AH minus 1. This condition is automatically satisfied because when you apply hx will necessarily be in the image, and then it's completely fixed. Here you will never have an element that is in the kernel. So you see that the J, you can choose anything. It just has to have value in image of A orthogonal. Let us now show the second condition that we want, that if we define U like this, it is indeed unitary. So we just use that it is an isometry. if I apply it to Z, an element here in the initial space can be written an element in the kernel plus an element in the image. So I write explicitly H of something. If I apply U to this element in the kernel, it is the isometry. If I apply U to H, I have UH. UH is A, so I have here JW plus AX. We see that JW is in the orthogonal of the image, and this is in the image. So those two vectors, they are orthogonal. So we use Pythagoras theorem. It is the square of this norm is equal to the sum of the square. J is an isometry, so it preserves the norm. We have seen this condition when we prove that the kernel of A equals kernel of H. We prove that AX is the same norm as HX, and now we see again that those are orthogonal. Here it's the direct sum of the other eigenspaces. So this element and this element in the image, they are orthogonal. So again, by Pythagoras theorem, this is the norm of Z. So you have that UZ equals Z. It is enough, in fact, to prove that U is a isometry, is a unitary. But if you want like more explicit proof, you can use the polarization identity. Here there is different version. If you consider that the sesquilinear map is linear in the first or the second variable. So here it's a bilinear map, and the polarization can allow you to write as a combination of quadratic map. This is something square. X plus y is something square. Because U is an isometry, it preserves the norm, and you can see directly that this quadratic form say will give this. This is x plus y, scalar product x plus y. Then you develop x minus y, inner product x minus y. You develop. So if we pause to think about what we have done, we have defined H, and then we have defined U by part. Now let us talk about the second method to do this. We approximate A by a sequence of invertible elements for which we have the polar decomposition. So we have already in step 2 established the polar decomposition for invertible matrices. And now we just need to show that it is possible to choose a convergent subsequence here, and that at the limit will still be unitary, the limit will still be positive. First step, so density of invertible matrices. It is basically the fact that the spectrum is finite. So we look at this polynomial in X, determinant of A minus X identity. So a root of this polynomial, it's a lambda such that this polynomial equals 0. And because this is a polynomial of degree n, it has at maximum n different roots. So the roots are the same as the eigenvalue, because if the determinant is equal to 0, it means that this matrix minus lambda identity is not invertible. Not invertible means that this lambda is in the spectrum. So you have a minimal distance between any pair of eigenvalues. In particular, you have a minimal distance. Distance is strictly positive between 0 and any of the other eigenvalue. So, 0 excluded. So if you take a complex number between 0 and the minimal distance that is strictly positive, the characteristic function polynomial, so applied to a lambda, will be different from 0. It means the determinant of A minus lambda identity is different from 0. It means that this map is invertible. So you even have a path that converges to A with all of those are elements that are invertible. A itself need not be. Of course, if you have a path, you can have a sequence. So here I just take in such a way that this lambda is smaller, strictly smaller than rho, than rho. Here p, it could be 0, but this will still be smaller than rho. So here we have a sequence that approximate A and all those elements that are invertible. So we can apply step 2, which is that we have the polar decomposition. We need now to show that the set of unitary matrix is compact. It is a subset of a finite dimension space of n times n matrix, so of dimension n square. So it suffices to show that it is closed and bounded. It is closed as the level set of a continuous map. The set of unitary matrix is when m star m equals identity. A single element is, of course, a closed subset of the set of matrices, topological space of matrices. So this is closed because this is continuous. Second argument, we show that it is bounded. So when M is endowed with the operator norm, it just means you consider a matrix as a linear map and you look at the maximum on the unit sphere or the unit ball, the closed unit ball. Here's a ball with a Euclidean Euclidean norm for vectors. But we know that a unitary matrix is an isometry. So if I consider the maximum when x is in the sphere, it will just give 1. When this is equal to 1, this is equal to 1. So the operator norm of u is 1. So every unitary operator is in the sphere of norm 1 of complex matrices. So it is the set of unitary matrices is closed and bounded. It's compact. By the Bolzano-Weierstrass theorem, we can extract a convergent subsequence. We write like this. We choose some indices, and the limit that we call u infinity, it is still a unitary matrix. So still by this theorem. So now we have chosen a sequence that converges to our matrix A. So any subsequence is also convergent. Here we have chosen a subsequence for U, and of course we have this condition UP HP. So H is completely determined by, we multiply on the left by U minus 1, A minus 1, A. Here we have extracted the convergence subsequence. So of course the taking the inverse is a continuous operation. Multiplication is convergent, is a continuous operation. So here it converges, here it converges, so the product will converge. It remains to show that the limit is still positive. In fact, I didn't really prove, but I have already said that positive necessarily implies Hermitian. I will write both, but it is in fact automatic. What is the definition of being positive? It means that this quadratic form of x is positive. Here we can see it as a function of the matrix inside. It is continuous. So when we take limit of x hx, it will be scalar product x, and here we put the limit inside. But you can just say that this is a number. The limit of a positive number is positive. So this is true for all x. It means that this matrix is positive. Same for hermeticity, self-adjointness. You can have an abstract formulation. You can say that this map is continuous, and then it means that the level set of 0, psi minus 1 of 0 is closed, because 0 is a singleton. And so if you are close, a convergent sequence has limit inside. So the limit should be inside. You can do also down to earth. You will have your sequence because those are self-adjoint. Psi of this is the 0 matrix. Psi of this gives 0. The limit of 0 is 0. It's a 0 matrix. And because psi is continuous, limit of psi equals psi of the limit. It means that the limit is psi of this is equal 0. It means the limit is Hermitian, self-adjoint. So now we conclude by saying that this is convergent, this is convergent. Limit of a product, because product is continuous, it is equal to product of the limit. So again, limit of the product is equal to product of the limit. We have shown that the the limit u infinity is still unitary, and here we have shown that the limit of the h is also still positive. So this is what we want to prove. Thanks for your attention, and meow.